in the local extreme case.
So you get rid of the negative 3?
I'm not going to get rid of them. I'm just not going to use them in the first derivative test. That's correct. I might need them for some other part of the problem, but not for the local extreme part. So first derivative test. Now, remember the domain you're on. You're on negative 3 to 3, so I got to include them anyway in the number line. The number line is truncated, right? And it's not an arrow to left and right, right? You have a restricted domain. So you're starting over here at negative 3, and then you've got a critical value somewhere over here called negative 3 root 2 on 2. You've got one here symmetrically opposite to it, right? At 3 root 2 on 2. I'm not going to put a 0 in here to show the symmetry because it's going to confuse you because you think that that is possibly a critical value, which it's not. And over here we've got the 3. Again, these are not here because I want to apply the first derivative test to these critical values. That's not why they're here. They're here because that happens to be the endpoints of the domain. All right? I'm not testing anything about negative 3 and 3 right now. I'm only testing around these two possible local extrema. So now what we need to do is we need to find out the sign of the first derivative on these three intervals. If it's changing sign, then these are going to be local maxes and mins. Okay? So I'm going to go back to my first derivative. Where is he? Okay, all simplified out, the first derivative is negative 2x squared plus x right over here. Oh, there's extra junk around it. 9 minus x squared to the 1/2. Okay, remember you're only looking for the sign on the derivative. So looking at this bottom here, forget plugging in numbers for a second. Just look at the bottom. Is it ever going to be negative? No, because it's the square root of something, right? Even if we do nothing else, certainly the bottom is always positive. So now I need to take a test case between negative 3 and negative 3 root 2 on 2. Is that? How do you know negative? How do you know negative 2 is over here? Maybe it's over here. Don't judge it by the scale I have on this thing, right? Can't go by that. You gotta pick a number between negative 3 and negative 3 root 2 on 2.
Negative 2.5.
Negative what?
Negative 2.5.
Are you sure that's far enough?
Yeah.
That's
Sure?
2.1.
Yeah.
That's 2.1 something.
Okay, well let's look at that. What's 3 halves?
1.5. 3 halves?
Yes, negative 1/2.
Yeah.
Negative 1/2. And you're multiplying it by something, so it makes it
It makes it more, which makes it 2.1.
it makes it further this way, right?
Yeah.
So
It's 2.1 something.
He wants something.
So the negative 2.5?
Yeah.
Fine. So take negative 2.5 and plug it in here. What will you get?
Oh, positive.
You're going to get a positive. How big is that positive? 2.5 times 2.5 is what?
4.5.
No, it is. What are you talking about? Yeah, jeez, you got to learn that. Oh.
What were you asking?
6.25.
Yeah, that's right. 25 times 25 is 625. So 6.25. Negative 2 times 6.25 is more negative than 9 is positive.
I don't know what you
Right?
did.
It's like negative 12 something. It's negative 12.5. Yeah, negative 12.5 sitting here. Plus 9, still negative.
Yeah, it will always be a negative because you have.
Ooh.
Well, I mean, in this case, between the intervals, because like negative 2 is like no, so you can take something like a positive one, but we're negative 2 is going to give you a positive output.
I don't know. We wanted to find
Oh, because I did this.
No, but once you add the 9, it might
And
make
that's
it
what
positive.
was.
Oh, I did not see that.
Yeah, there's a 9 there. Yeah, plus a 9. So we now know that it's negative on this interval. Negative. The first derivative is negative.
Still not 2.5.
What does that mean for original function? It means original function is decreasing. Okay?
That's 4.5.
So now you go in between these two. I've got a good number. It's called 0. Okay? So you put 0 in. That knocks this out. You got a plus 9. So it's positive. So first derivative is positive. I know the original function is now increasing on that interval. So therefore, since it was decreasing, right? It was decreasing. It passed through a horizontal tangent and started increasing. I must have passed through a local. Right.
Wait, I have a question.
So now I know. The answer is Poyo-Comparo. So local min at negative 3 root 2 on 2. There must be local min there. Right? Now, if we take the last test case, this last interval, and it ends up being negative, then I will know that it passed through a local max right here. So now we take our test case. Since the thing is symmetric, it's going to be. You'll pick something close to 3, like 2.5, and you will get 2.5 times 2.5, which is 6.25 times negative 2, which is negative 12 plus 9. Sound familiar? And you will get something which is negative. Since it's negative and the bottom is always positive, the first derivative is negative on that interval, which means the original function, again, is increasing. So it went from decreasing. So it went from increasing to decreasing right through that critical value, so therefore that is a local max. Now when I write this local max and min, that's the location of it. That's not the value of the min and the max, right? These are not function values as of yet. These are just the x values where this is happening. Right? I'm going to write local min and local max, just keep track of what's going on there. Okay? Alright, so we did not find local extrema. We found the locations of the local extrema. Okay? So local extrema, local min, is occurring at negative 3 root 2 on 2, comma, and I need the function value now. And local max, the same thing. So that takes a little more algebraic work. You gotta plug this back in the original function. So local max happening at 3 root 2 on 2, comma something. So if we take these values and plug them back into the original to get the actual height of the function, let's see what it is.
You're just plugging all the way back to x.
That's right. Yeah, back in the we need the function height now. So negative, what is it? 3 root 2 on 2. 3 root 2 on 2. Find that. Now, this problem is not as bad as it seems. We only have to plug in one of these, right? Once we plug in one, we know the answer to the other will just be the negative thereof. If you think about this expression here, right? The only thing that's going to change is the negative or positive on this first x. So once we do the first one, we'll have the second one automatically. So equals negative 3 root 2 on 2 times 9 minus negative 3 root 2 on 2 quantity squared. If I was smart, I would have taken the positive one first. We've got too many negatives here now. All right, so negative 3 root 2 on 2. What is the square of 3 root 2 on 2? 9 halves, right? I mean, that's where we got it from, remember? We had to take the square root of 9 halves. That's where we got this thing in the first place. So this is 9 halves. Agreed? 9 minus 9 halves is what?
Negative.
Thank you, Lee. Yeah. What's something minus half of itself? The other half, right?
Yeah.
Okay, so that means inside here is really a 9 halves. So we have negative 3 root 2, forget this one. Negative 3 root 2 on 2 times the root of 9 halves. But what's the root of 9 halves? 3 over root 2. So now we get negative 3 root 2 over 2 times 3 over root 2.
Why can't you just? Why can't?
What can I do what?
Why can't you just? Yeah.
The hell is that?
Insane.
It's the same thing.
Negative 9 halves.
No, it's
Negative 9 halves.
That was
So this one yielded negative 9 halves. This one, local max, yields positive 9 halves. Again, that's only because of the symmetry of this particular problem, right? Otherwise, we would plug in this one as well to find out the answer.
The 2 square roots.
That felt like I just did like.
Certainly, it's the same number.
Just
one over the other, right? Any number over itself is 1, right?
I thought after you rationalize it, you see what I mean? You go up to numerator.
Yeah, if I chose to rationalize it, but I don't need to. It's going to cancel automatically with that other one. I don't need to rationalize it.
Oh, okay.
See what I'm saying?